we first discuss how to mine multi-level association rules. Multi-level association rules come down to a very natural setting. For example, to your boss, if you say, now I found milk and bread sold together, probably everybody thinks this is common sense. But if you find 2% milk with a brand Dairyland sold together with Wonder Wheat bread, probably it becomes something more interesting. But if you see this Dairyland 2% milk actually sitting in a hierarchy, the top level could be milk, then go down to 2% milk, then go down to Dairyland 2% milk. So it is interesting to mine multi-level association rule patterns. Then the interesting thing becomes how to set a minimum support threshold. One way is we set a uniform minimum support threshold across all the levels. But there's one problem. If you set it very high, because they naturally have lower support, the low-level patterns will not show up. But if you set very low, the high level you get too many uninteresting patterns because everything may show up. So a reasonable way is set level reduced minimum support. That means items at a higher level, you use higher level minimum support like 5%. When you go down to the lower level, you may adopt lower level minimum support like 1%. To that extent, the skim milk will show up. At a higher level, some peanuts or some other things may not show up if they are not interesting, they are not frequent at all. So then the problem is, if we set a multi-level minimum support thresholds associated with different levels, then how can we use one scan in one shot? We mine all the different levels. The interesting thing could be we can use shared multi-level mining. We can use the lowest minimum support to let the high level pass down to the low level. But in the meantime, when we analyze rules, when we analyze patterns, we can figure out the higher level rules using higher level support threshold. So another problem for mining multi-level association rules is the redundancy, because the rules may have some hidden relationships. For example, suppose 2% milk sold is about 1/4 of total milk sold in gallons. Then, if you see these two rules, 1 and 2, the rule 1 says milk implies wheat bread with the support 8%, confidence 70%. But rule 2 actually dropped down a little from milk to 2% milk. In the meantime, the support also dropped down correspondingly, for example, from 8% to 2%. In that case, you probably can say the rule 2 is essentially redundant because we can derive such things from rule 1. Okay? That means if the rule can be derived from the higher level rules, the lower level rules are redundant, we should remove them. Another interesting thing is different kinds of items inherently may need different support threshold. For example, you go to Walmart, you may see diamond watch or some expensive things. They are more valuable, but they sold maybe less frequent. But milk and bread probably sold very frequent. So if we set minimum support for all kinds of items using the same minimum support threshold, then the valuable items may be easily figured out. So to that extent, it is necessary to have customized minimum support setting for different kinds of items. Okay. Instead of taking each item, try to decide their minimum support, we can use group-based, individualized minimum support. For example, we can group diamond watch or some expensive things, set up lower minimum support, take milk and bread, those frequent things, set up higher minimum support threshold. Then the question becomes how to mine such patterns efficiently. Actually, if we take our previous study, the scalable pattern mining methods, we can easily extend them by adding different minimum support threshold. I would not discuss the detail, but I think it could be a good exercise. Now we come down to another interesting issue is mining multi-dimensional association rules. Sometimes the items or the things we want to mine actually sitting on the multi-dimensions. The single dimension rule we studied, for example, X buys milk, then X buys bread. Milk and bread both are from the same kind of dimension called product. But sometimes we may get a multi-dimensional association rules. For example, for this interdimensional association rule, like if X age is 18 to 12, 25, and if X occupation is a student, then likely X going to buy Coke. That one actually, age, occupation, and items to buy are three different dimensions. That kind of rule we call interdimensional association rules. Then even we look at this, sometimes we see the hybrid cases. Like if X age is 18 to 25, if X buys popcorn, likely X is going to buy Coke. That kind of rule, you have age as one dimension, but these two buys are sitting in the same dimensions. Okay, so if you see this kind of cases, these three different cases may slightly need different kind of algorithms. Another thing is the attributes can be categorical, can be numerical. For example, the categorical case could be product like beer and diapers. And you may have profession like a student, professor. So for these categorical attributes, we can, for multi-dimension, interdimensional association rule, we can construct a data cube to mine such things, or just use data cube structure to mine such association efficiently. Then another case could be quantitative attributes, or we can say those attributes are numerical data. For example, age, salary, or some other things. For this cases, quite often we may use discretization method, clustering method, some kind of gradient approaches. We are going to discuss this part in the quantitative association rule mining. Thank you. Now we come down to study another interesting issue called mining quantitative associations. What is quantitative association? Quantitative association means some attributes actually are numerical data like age and salary. So how to mine such rules? There's one way is we can do static discretization. The reason we need to do static discretization is if you do not discretize them, you try to pairwise every possible age and salary, you will not be able to find any interesting or sensitive rules with sufficient support. But if we try to say we partition age every 10 years or partition income every $10,000 using some predefined concept hierarchy, we're going to be able to construct a data cube and we're going to be able to generate some interesting association. But these fixed predefined concept hierarchy may not fit your data distribution. For example, in the university, likely you may want to partition the age. For students, you may say it's 18 to 20, 20 to 22, or something like that. But for income, you may say $10,000 as one partition, or low and high. But if you go to hospital, their age distribution, you may like to say, middle age, old, or young. So another way is we do clustering based on data. That means we take every dimension, we study their distribution of the age and income, we perform certain clustering algorithm, generate a few clusters, and then we find the pairwise, frequent pattern of each such clustered pairs. Then finally, there's also popular way is to do deviation analysis. That means instead of doing fixed interval, we may do, based on certain condition like gender is female, we may find their mean or, like a median or something, some statistic measure. You will find if the wage mean is substantially deviate from the overall mean, then this could be an interesting rule. Let's go a little further to see how to find some such deviation. We also call extraordinary or interesting phenomena. Usually for this, we may say the left-hand side is a subset of the population, and the right-hand side is some kind of extraordinary behavior expressed using some statistical measure which could deviate from the overall. then the rule, whether it's true rule or it's just a very exceptional case, we need to do some statistic test like a z-test to confirm whether such kind of rule is of high confidence. Further, in many cases, you may even want to go deeper to get subsets of the population. For example, not only look at the gender as female, but look at the location is south. You may get the wage could further deviate from the overall mean, or even from the bigger rule like a gender is female. So that sub-rule could become an extraordinary sub-rule associated with its super rule. For example, sometimes you do not have the left-hand side as a subset of population, but you can, based on numerical data, you can group them into certain intervals or clusters. For example, the left-hand side could be if the education has pretty many years, like 14 to 18 years, and you will find the mean wage actually is substantially higher than the mean. So that may form another interesting quantitative rule. Efficient methods actually have been developed to mine such extraordinary rules. For example, one research paper published by Allman and Linder at KDD 99 is a very interesting case study or a very interesting algorithm. Now we study another interesting issue called mining negative correlations. So we first need to distinguish rare patterns and negative patterns. What is a rare pattern? Rare pattern usually means there are some rare occurring items. They have very low support, but they are interesting. We want to catch such patterns. For example, buying Rolex watches. How to mine such patterns? We previously already discussed this. Is for different item sets, like for those rare items, we should be able to set some individualized group-based minimum support threshold. That means for rare patterns, for just those items, we should set a rather low minimum support threshold. Then we will be able to capture such patterns. But negative patterns could be another very different one. Negative pattern means those patterns, they are negatively correlated. That means they are unlikely to happen together. So for example, if you find some customer, the same customer, who buys Ford Expedition, which is a SUV car, and also a Ford Fusion, a hybrid car together. So they are unlikely to happen together. So we call these patterns negative correlated patterns. The problem becomes how to define such patterns. We may have one support-based definition like this. We say, if the item sets A and B getting together, their support is far less than support of A times support of B. That means the chance they get together is far less than random. Okay. Then we can say A and B are negatively correlated. Is this a good definition? Actually, this definition may remind us the definition of lift. Then we may see whether they work well for large transaction data sets. Let's look at one example. Suppose a store sold two needle packages, A and B, 100 times each, but only one transaction containing both A and B. Okay. Then we will see these two needle packages, A and B, are likely negatively correlated. But when there are in total only 200 transactions in your data sets, you may see support A and B getting together because they got only one time. So 1 over 200, you get this number. This is a pretty small number. Okay. But then you look at support of A, which is 100 over 200 transactions. So it's 0.5. Same as support of B. So their product should be 0.25. So this number is far bigger than this. That means support of A and B getting together is far less than support on A times support of B. So we can easily say A and B are negatively correlated. They are negatively correlated patterns. Okay. But when the store sold in total 10 to the power 5, that means 100,000 transactions, then suppose all the others does not contain package of A nor B, then the situation could be completely different, because support A and B together is 1 over 10 to the power 5. But support of A now is 100 over 100,000, so you get 1 over 1,000. Support of B is also 1 over 1,000. Once they time together, you get 1 over 10 to the power 6. This number is even smaller than A and B getting together. Then you may say, oh, A and B getting together is very frequent, or it's positive correlated. Actually, it's not. What's the problem? The problem actually is null transactions, because there are so many transactions, they contain neither A nor B. They are null transactions. Okay, so we probably can see a good definition of negative correlation should take care of the null invariance problem. That means when two item sets A and B are negatively correlated, they should not be influenced. Okay, whether they are negatively correlated or not, they should not be influenced by the number of null transactions. Okay, now we give you another interesting definition, which is a Kruzinski measure-based definition. That means if we want to say A and B, whether they are negatively correlated, what we need to see is A and B are frequent, but the condition, the probability of A under condition of B and the probability of B under condition of A, their average should be less than epsilon, where epsilon is a small negative pattern support threshold. Then we can see A and B negative correlated can be justified for our needle package problem. We can see no matter there are in total 200 transactions or 100,000 transactions, if we say epsilon is 0.01, we can see this Kruzinski measure-based judgment. We can easily see the average of the conditional probability should be less than epsilon, so they are negative correlated. Okay. So this seems to be a very interesting and a good definition. And how to mine them? Actually, these are the methods similar to our previously discussed pattern mining method. We will not discuss it further. Now we are going to discuss another interesting problem, mining compressed patterns. We know frequent pattern mining may often generate many patterns, but many of such patterns may share some similarity, may be very scattered, but not so meaningful if you generate all those patterns. Let's look at such an example. Suppose we finally get 5 pattern IDs. So you probably see these 5 patterns are like P1 and P2. They are very similar, and their supports are also very similar. But P2 and P3, they are similar in item sets, but their supports are rather different. Can we compress them? We may first examine closed patterns. Actually, for closed pattern, there's nothing you can compress. The reason is closed pattern require the supports are identical, then you can compress them. But none of them have identical support counts, so nothing can be compressed. What about max pattern? Of course, we can use max pattern like P3 to represent all the patterns. But on the other hand, you probably see P3, this support is rather different from all the others. To use P3, you may lose a lot of information on the supports of other patterns. So the desired output actually is P2, P3, and P4. The reason you can see is P1 and P2, they share similar item sets, and also they share very similar support counts. So we may need a good measure to see what things can be compressed. The good measure could be pattern distance measure. We use this definition to define the pattern distance. You probably can look at P1 and P2 when we look at this. P1 and P2, their transaction intersection of their transaction ID. What should be the count? The number of transactions they can intersect? Actually, it's a smaller one here, because every transaction containing P2 must also containing P1. So their support counts intersection should be this number. Okay. What about the union? The union actually says all those transactions, because we know all the transactions P1 must also containing the transaction of P2. So their union number should be this number. Okay. In that case, we perceive these two numbers very close to 1. Then the distance 1 minus this very close to 1 number, you get something very close to 0. That means their pattern distance is rather small. Based on this, we probably can see we may be able to define a delta clustering or delta cover. That means if we can see the pattern P, the delta cover of pattern P is finding those patterns. All the pattern can be expressed by this. The distance is within delta. Actually, you probably see P2 is a good one because P2 essentially can cover P1 because P1 just have a little less item sets, but their support are so close to that extent, we may say they are within this delta cover. Okay. So for delta clustering, we will be able to cluster P1, P2 together using P2 to represent the pattern. So that means if we do this delta clustering, then all the patterns in the cluster can be represented by one pattern P. So the problem becomes whether we should mine all the patterns, then compress them, or we should directly mine these compressed patterns. Actually, there's an efficient method which can directly mine those compressed patterns. I'm not going to get into the detail, but you may refer to this interesting paper. Okay. Then another interesting thinking is redundancy-aware top K patterns. Okay. That means we want to get a desired pattern which is similar to the compressed one, is we want to get high significance and low redundancy, these kind of set of patterns. Okay. Let's look at this A, B, C, D, 4 different kind of compression. Actually, A is a set of original patterns. Their cluster shows their pattern distance, and the color, the darker shows it's more significant, the lighter shows it's less significant. Okay. In that case, you probably can see in this bigger cluster, there are 3 patterns. They are quite significant. If you just do the top K pattern mining, that means you take the support count or other significant measure, you will only find these 3 patterns. Suppose you want to only find top 3. Then all the remaining patterns, like here in the other cluster, is completely missing. But if you say, I just do the summarization, try to find clusters, and within each cluster, try to find their centers, then you probably will find those less significant patterns. So this may not be a good balance. Actually, better balance is you take care of both significance and the redundancy. Simply says, you look at this one, they are something very significant, and they are also in the cluster center. You may want to show these patterns. In the meantime, suppose you can only show 3, you may show these are significant and less redundant. This one is significant, and also it represents this cluster. So the problem becomes how to develop efficient and effective method finding such redundancy-aware top K patterns. There's an interesting study which uses maximum margin significance to measure the combined significance of pattern and develop efficient methods to mine such patterns. We are not going to get into detail of this method. Interested readers, we may read the paper we pointed out. Thank you.